Hello, this presentation is on final project submission of CS 683 course Advanced Computer Architecture taken by Professor Bishwa at IIT Bombay. Project title is Improving IPCP with Irregular Access Support using ISB. Team members are Arif Ali and Shomik Dotto. We are team Gandiva. Moving forward, problem statement prefetchers are used to prefetch memory so that we can mitigate memory wall problem. So IPCP is a special kind of prefetchers where we can prefetch based upon regular access pattern. By regular access pattern, I mean the difference between two consecutive memory access pattern is regular can be predicted well. But there are different access pattern like graph processing. There is uses irregular access pattern. For example, below this memory access pattern, there are no significant difference in the two consecutive memory accesses which can be tracked. But in long run, we can see this block is again repeating here. So this is a kind of temporal locality, and it's called irregular access pattern, which cannot be tracked by this IPCP prefetcher. Prior work are these two papers, one is ISCA 2020 and another is Micro 2013. This proposed bouquet of instruction prefetchers is a combination of four prefetchers which can be used in a different scenario. One is constant stride, another complex, global stream, next line. All these are regular, can track regular access pattern only. This irregular stream buffer ISB can track irregular access pattern. It uses a global history buffer which keeps this previous memory accesses so that it can track in future access pattern and prefetch based upon that. So our goal of this project is to integrate this irregular access pattern prefetcher into this IPCP bouquet of prefetcher, like that, so that we can prefetch or predict irregular as well as temporal stream also. Moving forward, we used ChamSim as a simulator here. These are some configurations of ChamSim we used. To highlight, we use single core processor, 4 GB RAM, 3 level cache. We did 50 million instruction as warm up and 50 million simulation instructions. Next, work done at checkpoint 1 we first integrated IPCP and ISB separately in ChamSim. Then we configured spec CPU benchmark and we did our primary result on the benchmark and we draw performance analysis. It's like this. Here these three prefetchers, one is IPCP, ISB and our combined IPCP ISB prefetcher. From geomin we can see with this combined one we got similar kind of speed up with IPCP and ISB, but no significant performance rise. So we moved forward, tried with different other ideas. We integrated accuracy based prefetch degree adoption, that at runtime we are checking depending upon accuracy we are setting the prefetch degree. We implemented confidence based counter, but it didn't found to be beneficial. We tested to combine the IPCP IP table with ISB metadata table, but it also didn't got fruitful. Then we refined the classification logics of irregular access class, that is the ISB class, with the whole IPCP class, and the benefit we found is like this. Here these are the different configuration we tried with IPCP ISB. This is train on miss, prefetch on all, train on miss, prefetch on miss. That is, we are training on only when miss is happening and prefetching only miss is happening, or every time. These are the global stride, constant stride, complex strides, and none is like we are prefetching with ISB when complex stride is there, when global stride is there, all or none is there. And this one violet color is we are using or prefetching with ISB with all other prefetchers when they are active. Also ISB will be used to prefetch. So from graph we can see that this violet one that this all is giving us the best speed up than the IPCP and ISB single-handedly. But one thing to note is that though with GCC we got better performance with this ISB one against that ISB and GCC, but in case of Omnet PP, this is an exception actually. In Omnet PP we can see that ISB single-handedly gave better performance than our combined one. So this was our area of discussion further, how to handle both these cases so that we can get the best in both of these traces. Next, work done at checkpoint 3, we again brainstormed and refined the classification logic a bit further, and finally we found a sweet spot to handle the GCC and Omnet PP gracefully together. We also adjusted and played with those buffer size, stream length, but that didn't give any benefits. And finally, in this checkpoint we are giving the final take on our final optimal bucket of prefetchers, and we will give the accuracy, coverage, MPK of updates also to support our state, and this evaluating the contribution of each prefetcher in the bucket of prefetchers. Next is this is the version 3 graph, where now this version 3 graphs is getting better performance than IPCP and ISB. And point to note is here we have handled within GCC also we are getting better performance than IPCP and ISB, and we handle the Omnet PP case also, where in Omnet PP also with our new configuration we are getting better performance than IPCP and ISB single-handedly. So is the all over the till now the best and optimal performance we got. So but these two versions, which one to take and go ahead with is a little bit, there are trade-offs, so that mysteries will be revealed by Arif.
So for choosing between those two configurations, we took some statistics for two traces. Mainly we are looking here we are looking for Omnet PP, and for Omnet PP we are aiming to get the the speed up, because only IPCP is able to get 3% speed up and ISB is able to get 30% speed up. So we are trying to at least match ISB's performance. So the main takeaway of this statistics are these two metrics, that is address table size, which is for the first case it is 380k and for the second case it is 385k. So even though you are seeing more number of IPs and addresses, the address table size is mostly similar. But another interesting point is this prefetch issued thing. So we are seeing that almost 11.7 million times we are issuing prefetch, and only for the second case we are only prefetching 7.7 million times. So why is this happening? So what we think, and also we later confirmed, that because it is actually getting more matches in the structural address, like structural address is existing, but the stream actually, after we are getting a match, the further the stream that is there, it is not contiguous, it is like there are holes in the stream. So that's why it is not able to prefetch that many addresses. So next we did a small micro benchmark to support our theory. So we ran the configuration for 5 million instructions, and we saw that for degree 8 we can for the first configuration there are 5000 times which is it is able to prefetch, but for the second configuration it is only able to prefetch 500 times. So this confirmed our guess that indeed that is what is happening, it is not able to get the contiguous stream. And also for the second case it is mostly prefetching less number of times, like the count for the less degree is comparatively more for the second configuration. So that is why we are getting getting the speed up for the first case on Omnet. Yeah, so this is GCC, and for GCC we are already getting most of the speed up by IPCP. So here what we focused on is how to manage the space. Like the best configuration gives around like 4.11 speed up, but it is the space is like 2.5 million addresses, but it is 8 times than the first configurations, and when going on the first configuration we can get decent speed up, but the space savings is huge. So finally we are going on with the train on mesh and prefetch on all configuration for the both reasons on the space and the speed up. So this is our final take on the improved version 3 speed up on the various traces. Like we are able to get this combined prefetcher which is better than both the IPCP and ISB alone on the we can see on the geomin. So next, this is the accuracy numbers. So here actually, since we are not focused that much on what we are prefetching, we are actually not getting that much filtered out request, we are not filtering. So actually the accuracy is bit low than ISB alone, and so here we'll see in the next graph that we are actually trading the accuracy for to get more coverage. So and getting more coverage resulted us in getting the speed up actually. So on the geomin you can see that the coverage percentage is more for our combined prefetcher. Yeah, so similarly MPKI numbers are also as expected. Our combined prefetcher has the lowest among the baseline, the IPCP and the ISB prefetcher. Yeah, so this is an interesting plot. So we tried to find out like what is the individual contribution of different classes. So as expected, we are seeing for Omnet, we are seeing that mostly the speed up is gained from the ISB class, ISB code, ISB prefetcher. But for GCC we are seeing that very less is for ISB and mostly it is for the GS class which is part of IPCP. So we can see that wherever ISB is good, like for Omnet PP and Salang, and also for some part of Soplex, we are getting its speed up, and wherever IPCP is good for libquantum and GCC, we are getting its part also for Sphinx 3. So we are able to get the best of the both of these prefetchers, which is being shown this from the class wise utilization. So overall insight is this, like our motivation was we can since IPCP already has a spatial part, so but the most traces have a mix of both spatial and temporal locality. So somehow can we get also cover the temporal locality part. So for that ISB is there, so that's why we try to integrate these two, and actually are getting performance increase, which is the hybrid solution. We can get the strength of the both world. Wherever the spatial prefetcher is required, IPCP is triggered. Wherever the temporal prefetcher is required, ISB is triggered and is able to deliver performance advantage. For the future work, we can still there is a scope for still minimizing the storage footprint for ISB, because it is a temporal prefetcher and it requires a lot of storage, because it has to remember the reference stream, because it cannot there is a no same stride, so we have to mostly remember the streams and prefetch based on it. And so maybe what we can do is not having all IPs remembered. We can, by some filtering mechanism, we can have some critical IPs for which we will be maintaining the streams and prefetching based on that. So by that we can lower the footprint of the memory a lot. Also we have only done a very limited amount of benchmarks on the traces, so we can also do comprehensive testing in the future to get more deeper insights. So these are the walkthrough of the code. these are the our code repository in the GitHub. So this is the default ChampSim directory structure. So inside prefetcher there are our different versions, like we are seeing the IPCP L1D prefetch. This is version 1, and this is the version 2, and version 3 is this one, which is the latest one. And mostly these are the parts of the IPCP and its associated structures, and where our the ISB part, this is where it starts. So ISB code is plugged in here. We don't have very different inside this code section, only we are just changing when this part is being triggered. So as we discussed, it is being trained on miss, and it is triggering every time whenever a structural address is existing, it will prefetch. That is what we are calling as prefetch on all. And after that, it is the next line prefetcher, which can be as before, it can be triggered, and we have not changed it methods. So yeah, that will be the mostly of the crux of the parts, and these are the just printing of the statistics part of ISB and other prefetchers. Yes, that will be the part of the code walkthrough of the and here is the most of the other checkpoint works and what we have proposed and what we have done still now. This is the readme, and yeah, this is a GitHub link, and yeah, thank you.